This lecture will cover Chapter 6, Section 6.3, and the title is Modeling Continuous RVs. And no, we are not taking a road trip, although it would be fun. Okay, I want to start by reviewing a key concept, the distribution. When we make decisions or estimates in statistics, we always calculate probabilities. Type 1 and Type 2 error, for example, p-values, and soon the confidence level for what we call confidence intervals. Now, I want to spend a minute talking about the frequentists. This comes up in the book I asked you to read, or I recommended that you read, The Lady Tasting Tea. Ronald Fisher, who is credited in a large part with developing what we think of now as statistics. Some think of Ronald Fisher as the father of statistics, and he wrote the first actual textbook in statistics. But the question about probability was a question he had to grapple with. And it turns out throughout the history of mathematics, well, I don't know if it goes back that far, but at least for the last couple hundred years, mathematicians have really struggled with the philosophical interpretation of what probability really means. And I think in our popular culture, we use, and in our society, we use and talk about probabilities. 20% chance of rain. There's a 50-50 chance something might happen. Those are probabilities that are calculated in different ways. Sometimes probabilities are what we call personal probabilities. You might call up a friend and say, hey, are you coming over today? And your friend may say, well, there's a 60% chance I can come by today. That is a personal probability, and it gives us a sense for how likely it is that something's going to happen. For example, if your friend said, well, there's about a 10% chance I'll come by, you're probably not going to change your plans to make sure you're home. On the other hand, if your friend says, yeah, I'm 99% sure I'm going to come by today, well, that means it's very likely your friend will come by. But again, those probabilities sometimes that we throw out there aren't really based on anything mathematical. They're just based on some kind of an intuitive, conceptual kind of, actually what it really is communication. We're communicating an idea. Now, in statistics, though, we need to add more rigor to the calculations in order to give our probabilities credibility. For example, if I made a decision based on some statistical hypothesis and I said, yeah, chance of type 1 error, that's 12%. And then a critic comes along and says, hey, Todd, where'd you get that 12%? Well, gee, I just made it up. That doesn't really have any rigor. And so in statistics, what we need to do is we need to establish some assumptions, calculate these probabilities based on distributions, as it turns out. But one of the key concepts is once we get this probability value, what does it mean? How do we interpret it? That's where the frequentist interpretation comes into play. And this frequentist interpretation is the traditional way we interpret what probability means in statistics. So what is the frequentist interpretation? The frequentist interpretation is what will happen if the statistical study repeated over and over and over and over and over and over. So for example, when we say the type 1 error rate is 5%, it means if that hypothesis test were repeated many, many, many times, one time out of 20 would result in a type 1 error. But we're only going to look at one set of data, so we're never going to know whether or not we've actually made a type 1 error. All we know is the relative frequency with which type 1 errors happen using the techniques that we're using. our interpretations rely on the relative frequencies of these events. So again, you have to use your imaginations here. You have to understand that, yes, we only have one set of data, but when we interpret the probabilities, like for example, a p-value from that set of data, those interpretations rely on this relative frequency concept or this frequentist interpretation. Let's go back to this Salmon data set for a minute and start talking about distributions. So I made up this problem like I admitted earlier, but let's just go with it. Here's the story. A field biologist working for the California Fish and Game recorded the following weights for 33 king salmon caught by sport fishermen out of Humboldt Bay. So here are the weights. Now, when we think about the distribution of the data, what we can do is draw a histogram. Now, what you have to keep in mind with the histogram is that we're only looking at 33 data values. So n equal 33 for this case. And what we can do is divide up the domain into classes, etc. And then this bar, or this y-axis, these are the frequencies, which means, which means how many of the data values are in each of these particular classes. And the histogram works really well when we have relatively small and what do I mean? Less than infinity. When we have relatively small samples or relatively small numbers of values to deal with. But when we start thinking about drawing a histogram for the population, what's that going to look like? Well, how many salmon are there? I think the answer to that question is, so here's my question, how many salmon are there? The answer is nobody really knows for sure. Now, you scientists, biologists, fisheries biologists could make an estimate of how many salmon are out there, and that happens, I think, all the time, and there are techniques for doing that. But at the end of the day, nobody really knows for sure. Okay, but capital N, the population size for this is, I think it's safe to say, really, hopefully at least, really, really big. So what's really, really big? Well, I don't know. Are there 1 million? 10 million? So when we're talking about populations that are in the millions, and many populations that we deal with in statistics are very large like this, then there's really no way to draw a histogram. Like, for example, if I set up a graph with the same scaling, right? So x is the length of a the weight of a randomly selected salmon. And again, we could, for the salmon population, I could divide up that domain. 0 pounds is probably going to be, we know we won't have any salmon less than 0 pounds, right? But now as I begin to fill in this histogram, okay, I'm going to need a frequency axis. Okay, y for frequency. And so suppose I'm looking at the category here, and again, I could continue this scaling, but I want to just talk about a single class. Say this class, all the salmon between 15 and or 10 and 15 pounds, including 10. So what we could do is draw this bar, right? Okay, so if we could go out and catch every salmon in the ocean and the river and wherever they might be, we could, hypothetically, we could count all the salmon in this class, 10 to 15, and then we could put a number up here. But in reality, I can't really do that. So I don't actually really know what number to put here, okay? So there's really no way, well, all right, so if we have a population that is tractable, meaning that we could sample every single member, and you know, sometimes in statistics those populations exist, then yes, we could do this. We could conceivably sample every single member of the population and draw a histogram. But in many practical situations, we just really can't do that. So in this particular example, I made up the population. And that's really helpful because I can do mathematical things now. So I randomly sampled the salmon data from a known distribution, okay, I'm using some notation now to describe this notation. And what this means is N for normal, so I'm saying the salmon weights are normally distributed with a mean of 30 pounds and a standard deviation of 50 pounds. So the 30 is mu and the 5 is sigma. Now, here's the notation right out of the book. X is, the variable X is normally distributed with the population mean mu, population standard deviation sigma. So in this case, X is the weight of a randomly selected salmon. And so what I'm saying is X is normally distributed with a mean of 30 and a standard deviation of 5. Now, what's the probability? Well, okay, so if we were talking about the n equal 33 data set, and I wanted to know the probability that X from this data set equaled, say, oh, I don't know, 10. And again, I lost my scaling here, but this is like 5, 10, 15, 20, and so on. And let's see, suppose these heights right here are, can't remember how high those are. Let's say that's 2. I think that was 2 right there. No, actually, that must be 1. All right, so there was 1, say there was 1 data value in this class. So, oops, I didn't mean to put that parenthesis there. Hold on, let me redraw this notation. I meant to write probability X is equal to 10, say. Well, I could say that's approximately equal to 1 out of 33. But again, this would be a really contrived situation because really technically what I'd be doing is sampling from a sample, okay? And we could do that, but that's not really a practical thing. What we're doing is we're trying to sample from the population, okay? So when we move to the population, okay, so let's talk, this is from the data, let me be clear here. So this is, the histogram is showing the distribution of the data, and when we want to talk about the whole population, we have to think more abstractly. And first of all, we have to think, okay, same variable, X is equal to the weight of a randomly selected salmon. Okay, so same thing here. But now, suppose we calculate the probability that X is equal to 10 for the population. Well, this is going to equal a really small value. Okay? So even if I was thinking about the population as being finite here, which it is, the probability of catching a salmon that's exactly 10 pounds is very unlikely. But it gets even more complicated. And this is where we have to start using our imaginations, okay? So let's go back and talk about X again. So what's the domain of this variable? And this is where we go back to algebra and we go back to these theoretical, abstract mathematical ideas. So the domain are all possible salmon weights out there, okay? But we're going to model this using a hypothetical mathematical set called the set of real numbers. And in a previous lecture, I talked about George Cantor and the size of the reals being bigger than the size of the integers and so forth and so on. But this domain, this set that we're talking about, is uncountably infinite. What does that mean? Well, it means that there are more real numbers in that set than we can possibly imagine. But the idea here is that X is a member of R, meaning X, now we're talking theory here. Okay, this is theory. This is abstract. Okay, and these are based on assumptions now about the population. Okay, so this now implies that if we're now that we're going into this theoretical abstract part of the class, X equaling 10, the chance of sampling a single value like 10 from an uncountably infinite set, now I'm using an equal sign too, is 0. It just isn't going to happen, okay? Now, what that does is it really informs how we're going to have to model the population, okay? So we're going to model the population, and we're going to model the population using a continuous smooth curve. And the curve that we're going to use, the distribution, now I'm using the D word, modeling the population. All right, let me just write that up there. This is where we're talking about the distribution, what we call, distribution. Let me spell that again. Distribution. Okay, so now when I draw this x-axis, okay, what you have to keep in mind is I just drew the domain. X is a member of R. So when I draw that axis, I'm drawing, what you have to imagine is this is the set of all real numbers on this axis. Now, when I draw this curve that we call the bell curve or the normal curve, and mathematicians like to call it the Gaussian, because Carl Gauss is the mathematician who first thought of this family of curves, what we do is we say, okay, well, the weights of salmon are following a normal distribution. So that curve is the N35 curve, okay? Oops, not 55, N35, which means, again, I can start to scale this. So 35, 40, 45, 50, so on. And then, of course, we'd scale the same way back this way. So the domain here, or the axis for the histogram, okay, is similar to the axis for the bell curve, okay? But with the bell curve, we're not necessarily creating classes, okay? Each point on the x-axis, and this is the idea of a smooth and continuous curve, every x value on this axis has a corresponding y value on the curve, okay? But, and this is important, the height here, okay, when we're modeling with these continuous curves, this height is not a frequency or relative frequency. So as we begin to deal with these continuous variables and model these continuous variables, we have to keep in mind now where with the histogram, okay, the heights here, okay, the heights for the histogram were frequencies, okay, yes, these are frequencies for sure, but for the normal curve, the heights are not frequencies. So the Gaussians, I'm calling these the Gaussians. Statisticians call these bell curves, okay, because they look like bells. And again, I think in statistics there are lots of synonyms. And what bell curves or even normal curves. But all of these words we're referring to as the set of normal distributions. Now I will mention though the Gaussians the set of Gaussians have more curves than just the normal curves. The actual normal curves is a special case of the Gaussians, but that's a whole nother pure math kind of concept that I'm not really going to get into in this class. Now, okay, couple of characteristics of the bell curve, okay? The bell curve has, right at mu, a vertical line of symmetry. Okay, so if you notice right here, right down the middle, if I folded this curve right down the line, right down there, that vertical line that cuts down through mu, it would line up perfectly on both sides. That's what we mean by symmetry. Now, point of inflection. What is a point of inflection? Well, points of inflection occur where there's a change in curvature. Notice in between this gray area, okay, let me change my pen color here. Oops, come on. Okay, so in between, within one standard deviation, okay, so what's happening down here on the axis is that when I take mu and I add sigma, and when I subtract sigma, what I'm creating is a one standard deviation window. So this set that we're spanning right here, from here to here, using interval notation, I would write mu minus sigma, comma, mu plus sigma, okay? So with the previous example, with the normal distribution 35, for example, then this interval would be, so I'm just going to use some real numbers here just so you can see it. So 30, this would be 35, and this would be, that's a 3, and this would be 25. And so the actual interval for the salmon population would be 25 to 35. Okay, but now the point is, notice that the curvature here is concave down. Okay, so this part of the curve is concave down. Now, when we get down, now the definition of point of inflection, okay, and that's a point on the curve, that's that one instantaneous place where the curve goes from being concave down and then it switches to concave up. Okay, so now the curve is opening upward. We call that concave up. And again, over on this side, the curve is also concave up. Now that change in concavity always happens at a point of inflection. Okay, and for the normal curve, the point of inflection or the change in concavity always occurs for a normal curve at the one standard deviation point on both sides. So that's a characteristic of one of the characteristics of the bell curve. And what this does is really one thing this does is it helps us draw the curve. Now there's many different bell curves. And what do they have in common? Well, all of the bell curves have this vertical symmetry. Notice. Okay. And they're all, oops, hold on now. Okay. And all of those all those lines of symmetry are happening at the population's mean. Okay, so these are three different possible curves. So this first curve has a mean of 50. So notice if I come down here to if I examine the curve, there's a line of symmetry right there at the mean 50. Same thing here. Okay. And then the other characteristic that the curve has, and again, remember we needed two values to uniquely define a population. One was a measure of center, that's the mean, and then there's this measure of spread, okay? So the larger the standard deviation, the more spread out the curve is. The smaller the standard deviation, the narrower the curve is. So every normal curve needs two parameters. Remember, mu and sigma are parameters. Two parameters. You need a measure of center and measure of spread. So every normal curve has these two parameters, mu and sigma. Without mu and sigma, I don't know which particular normal curve that we're talking about. Now, I've also referred to the empirical rule, and this is another characteristic of the normal distribution. If you go one standard deviation, so remember, again, if we were talking about the Salmon data, okay, let's just put some numbers on here. So for the Salmon data, we had n was 30 was the mean, and the standard deviation was 5, okay? So I'll put those numbers. I just want to scale this axis just to give one concrete example, okay? Because I know students often get confused with the mu plus sigma minus sigma, but notice what mu plus and minus sigma means for our Salmon example is I'm taking 30 plus 5 to get to 35, and I'm taking 30 minus 5 to get to 25. So the interval 25 to 35 spans about 68% of the population. And similarly, the interval from, let's see, I'll go another standard deviation here, and that's going to take me to 20. And I'll go another standard deviation here, and that'll take me to 30. So, or I'm sorry, 40. So the interval from 20 to 40 spans 95% of the population. So when we sample a data value that's beyond two standard deviations, okay, we call that an event rare and unusual. So let me say that again. When we sample a data value that's more than two standard deviations from the population mean, then we say that's a rare and unusual event because 95% of the population lives within two standard deviations. So when I'm beyond, when my x value is beyond that threshold, we call this rare. We call this rare, unusual. And then this range within two standard deviations is what we would call typical. So if you want to use the alpha equal 5% rule, this is Fisher's rule of thumb, then this is really what we're talking about here. If we've got 95% in between, that leaves 2.5% in each tail of the population. So when we're dealing with a value that is beyond two standard deviations in either side, then we're in the 2.5% range of the population, and we're going to have to call that data value rare and unusual. Now, it's not as cut and dried as that. We can certainly calculate things like p-values and get a more refined probability of getting the data. But this is like just a general kind of convention or rule of thumb. Okay, so let's try to put these ideas to work here and start talking about a different actual population. Let's talk about, this example comes right out of the book. This is the Let's Do It 6.5, and we're talking about the distribution of pine needles. So different species of pine trees are grown at a Christmas tree farm, and it's known that the length of the needles on a species A pine tree follows a normal distribution. And we're also told that about 68% of such needles have lengths centered around the mean between 5.9 and 6.9 inches. So we're asked, what's the mean and standard deviation? Okay, so a little bit tricky to figure out here. I'm going to draw a little tiny graph here to kind of hopefully illustrate this idea. So we're talking about we're told that the distribution's normal, okay? And we're not told what mu is here, but what we're told is that 68% of the population is centered around the mean between these two values. Well, so that means the mean's got to be dead center between these two things. So that would be, well, let's see, 6.9 minus 5.9 is 1 divided by 2 is 0.5. So this should be 5.9 plus 0.5 makes the mean 6.4, okay? And then the standard deviation, again, remember what I'm basing this whole analysis on is this 68% rule here within one standard deviation. So that means the standard deviation is the distance from 6.4, for example, to 6.9, which is 0.5. So X here is normally distributed with a mean of 6.4 and a standard deviation of 0.5. So now this gives me the theoretical model for the population. Okay, and again, given in the problem. Now, for part B, we're asked to calculate, whoops, let me go back there. We're asked to calculate, so we're told that a 5.2-inch pine needle is found. It looks like it's species A needle, but it's somewhat shorter. Is it likely that this needle is from a species A pine tree? And then the hint is calculate the proportion of needles that are 5.2 inches or shorter. So let's talk a little bit about this. So we're told what the distribution is, okay? And so let me redraw that. Okay. Try to draw neat graphs. Okay, I'm going to start over on that graph. I didn't like it. All right, let me try it again. These are sketches, so, you know, make them as neat as you can, but, oh man. All right, that's not a very good normal curve. I don't know why I'm struggling with this one. I'm going to try it one more time. It takes some practice. I think I'm out of practice here. And you want to go up, down. All right. Good enough. All right, so 6.4 is here, okay? Now, and then we also know that, let's see, and the way I'm drawing the curve is I'm kind of looking where I drew the point of inflection to get the scaling right. So I'm seeing how I drew this, the curvature is kind of changing right in this area. So that's where I want to put the 5.9 value. And the same thing over here, curvature. And then I'm kind of eyeballing to make sure these are roughly the same distance here. And then I can continue to scale my graph accordingly. And again, I'm just finding these values by adding 0.5 and subtract. Of course, on the left, I've got to subtract 0.5 to get these other values here. So let's see, what would that be? 5.4, 4.9, and so on. Okay. Now, this is a density curve, what we call a density curve, okay? And the total area under this curve is 1, okay? And this makes sense, all right, if you think about it. It means that the curve spans the all possibilities for the population. Now, one way to think about this, okay, now the data value that we got was 5.2. So 5.2 is a data value right about here, on that x-axis. So we can see already that that 5.2 is greater than 2 standard deviations away, okay? So the proportion, so based on the empirical rule, the proportion of x's less than or equal to, and the way to think about this is when we say the proportion of x's in this case less than or equal to, these are the x's that are at least as extreme as 5.2, okay? So what proportion of this population is at least as extreme or unusual as 5.2? And we can say that that proportion that we're talking about is now this proportion is less than 2.5% based on the empirical rule. But we want to do better, okay? Let's be more specific or precise. Okay, because this is mathematics now. So here is the key one of the key concepts for these continuous distributions like the normal curve, okay? And this is an idea that is abstract and sometimes hard to understand. But the proportion of the population, the proportion is the area, okay? The proportion is the area. So this area in the tail of this distribution that I just shaded is the proportion, okay? So to find the proportion, okay, let me write it over here. To find the proportion and the proportion I interpret, or we interpret, as a relative frequency. To find the to find the proportion means find the area for this type of problem, okay? So how are we going to find how are we going to find this area? Well, let's do some notation. So we're going to say P of x less than or equal to 5.2 equals, all right, here comes the calculus. It's the integral from negative infinity to 5.2 of the function that defines this curve with respect to x. So this curve is drawn as a y equal f of x function, okay? If I knew the function and I knew the calculus, I could find the area using this thing called an integral. However, we're not going to do that in this class, okay? Although this is the problem we would have to do. So calculus is behind the scenes when we do these types of problems, okay? Turns out there's a built-in function on the calculator that does this integration for us. And that function is called normal CDF, okay? And of course, normal stands for the normal probability distribution. CDF stands for cumulative density function. So this cumulative density function does the same thing the area does, or this integral does, which is find the area starting way out here at negative infinity, okay? Because this curve is asymptotic. It goes all the way out to negative infinity. And then we're going to go on, and then we're going to go up to the x value 5.2. So if we were going to do this on the calculator, then I would put in negative infinity, comma, 5.2, comma. Now, we need the parameter values. Mu and sigma are what go into this calculator function next. Okay, but we have a problem. We have a problem. Okay, the problem is there's no infinity key or button or whatever on the calculator. There is no infinity feature on the calculator, okay? And that's a little bit of a problem here. So let me talk, I'm going to talk about that as we go to the calculator. So let's switch gears here for a minute, and I'm going to bring up my calculator and show you on the calculator where these features and these functions are hiding. Okay, so notice above the vars key in blue, you see DISTR for distribution. When we press second vars, okay, we come up, what we see is a menu that gives all the built-in distributions, okay, for all of these probabilities that we might do. Now, PDF and CDF. Notice there's two here, normal PDF and normal CDF. PDF, you're probably never going to use PDF in this class. I might use it on occasion as a demonstration, but normal PDF will not calculate probabilities. What normal PDF does is draw the normal curve. We're looking for normal CDF, and normal CDF is what actually finds the areas under the curve, and that's what we're looking for here. So I press enter on that, it comes up on the home screen. I have to enter some values. Now the deal is that what I need to enter, technically what I need to enter mathematically is negative infinity. But there is no negative infinity key here. So what I'm going to enter is a really small number. I'm going to enter -1, second function EE. That means, that's scientific notation. This means -1 times 10 to the 99th power. That is a really small number. Still, technically, in an abstract way, that's not even close to infinity, but it's far enough to the left on our axis that it's going to give us really good results. Next thing I enter is the x value, 5.2. Then I need to enter the mean and the standard deviation. I'm going to pop back to PowerPoint here because I forgot. The mean is 5.4. Standard deviation is 0.5. I needed those two bits of information, 6.4 and 0.5. So the mean is 6.4 and the standard deviation is 0.5. Okay, so once I've entered all those values, I press enter, and what I end up with is 0.0082 approximately. So what that tells me is, I think that was about 0.0082. So the proportion of x's at least as extreme as 5.2 is approximately equal to 0.0082, okay? So that means that we would only sample x's this extreme from the specified population about 0.8% of the time. Less than 1% of the time. So that most people would interpret a needle as extreme or more extreme than 5.2 on the left as being rare and unusual. Now let's talk about the standardization transformation for a moment here. So if our x value is normally distributed with a mean of mu and a standard deviation of sigma, then the standard normal variable z is equal to x minus mu over sigma, and z is n0, 1, okay? So for that pine needle example we just did, x is normally distributed with a mean of 6.4 and a standard deviation of 0.5. If we take x and we process it through this transformation, okay, and I'm going to replace the mean, the arbitrary mu, or the unknown mu with the known mu in this problem of 6.4, and again sigma is 0.5 for this example. What we've done is we've transformed x to z, and then z is n0, 1. So let me try to draw a diagram of what's happening here. So first of all, the axis we're talking about originally is an x-axis, and there's a normal. Of course, the population has a normal distribution, and the population's distribution is centered at the mean 6.4. And again, I'll put a few other x values on the scale here. Okay, so this is the n 6.4.5 distribution. And then we pass this through the z transformation above, okay? So we're going to pass the x value in question, or theoretically what I'm saying is transform all x's, okay? All the x's. And what do we end up with? Well, we end up with a related distribution, and this is because z is a linear transformation. That concept takes us back to what chapter was that? Chapter 5, right? Where we were talking about the properties of a linear transformation. But what's happening here now is this distribution, this mean of 6.4, when I take it through the transformation, is mapped to 0 on the n0, 1 distribution. So notice a couple of things here. The label on the axes I've changed, okay? Because all the x's are coming through this transformation now to the z distribution, okay? So the mean 6.4 goes to 0. The x value 6.9, that was one standard deviation away from the mean, remember? And then that 6.9 is getting mapped to 1. And 7.4 gets mapped to 2. And 5.9 gets mapped to -1, and so forth. So this entire domain for the x distribution, okay, pine needle lengths, gets mapped over to the z distribution. So what ends up happening here is that 5.2 value that we were interested in, okay? So the probability or the proportion of the distribution that's at least as small as 5.2, okay? Now, if we take that x value in question, the 5.2, okay, and we pass that through the transformation, what does that give us? Well, I'm going to get out my calculator here, do this calculation. So I'm taking 5.2 minus 6.4, and I'm dividing that by 0.5. So that's -2.4, okay? So that z value now is, so let's see, I'll put a -2 here, and then negative 2.4 is say right about there. So here's the key idea, okay? These areas are the same. So the area under the N6.4.5 curve is the same as the area under, or to the left of, negative 2.4 in the N01 distribution. To look at this in a different way, going back to the calculator, okay, we did the normal calculation for 5.2. So now what I'm going to do is I'm going to go in here and I'm just going to edit what I had originally, and I'm going to change it to the z distribution. So what I'm doing now is I'm putting negative 2.4 in, because that's 5.2 transformed to the standard normal distribution. The standard normal distribution always has a mean of 0 and a standard deviation of 1. So now press enter. I get the same probability. That is useful because what it means is we can take any normally distributed can't spell that word, distributed, any normally distributed x and transform it to a standard, or to a standard normal distribution. All right, so what does that mean? Well, all right, when I'm in X land, okay, there are many possible normal distributions. And technically there are an infinite number. So there are an infinite number of possibilities. And each one of these particular possibilities, I think I'm spelling that right. So there are an infinite number of possibilities, okay? All of those x's can be transformed using the standardization transformation to a standard normal variable z. So any of these in X land going, and again, I'm talking, the X land, I'm talking about X distributions. There are many different possibilities. Pass those x's through the standardization transformation, and we transform any of those variables to what we call a standard distribution. Now, if you think about creating a standard normal distribution, it's a lot of sense in centering that thing at 0. If we had to pick, if we were going to pick, now again, I could create a transformation and make the mean for that transformation any number I want, okay? But if we're talking about a standard place to center, to transform any possible x to a standard, kind of makes sense to have the standard or the mean be or have the distribution centered at 0, the mean be 0. And it also kind of makes sense to have the unit as the measure of spread. And that's exactly what happens when we standardize. Now, this z transformation is important because as we move through the material, what we're going to do is enter into the realm of hypothesis testing. And this concept of standardization is useful because it can give us one type of hypothesis test. Since all of these normal variables can be transformed to one particular distribution, that gives us a uniform, well, I don't want to use the word uniform here because you'll think uniform distribution, but this gives us a consistent or a what's a good word? A consistent or a standard. Standard is the word. It gives us the standard distribution we can use to calculate probabilities. Here's an example of how we might use this idea of normal distributions to actually do a hypothesis test. And I really like this example. It's kind of fun. A man is shot and killed while hunting in North Forest. It looks like an accident, but police question another hunter who is known to have had a grudge against the victim. They find a pine needle stuck to the suspect's coat. The suspect claims to have been hunting in South Forest on the day of the incident. North Forest has only species A pine trees. South Forest has only species B pine trees. Species A pine trees have needle lengths that are approximately normally distributed, with a mean of 5.4 centimeters and a standard deviation of 0.4 centimeters. Species B pine trees have needle lengths that are approximately normally distributed, with a mean of 6.4 centimeters and a standard deviation of 0.5 centimeters. The prosecution hires you to be the expert statistician. You are to test the following statistical hypothesis. Now, this follows the same pattern that we use in a criminal court system. The null assumption is suspect's not guilty. Alternate, guilty. So the question is, how rare and unusual is the evidence? And what's the evidence going to be in this example? Well, it's going to be the length of the pine needle. Okay, so first thing, same variable, two possible populations, okay? So x is the length of a needle, and we're asked to draw these two distributions on the same axis. So I'm going to draw an axis here, okay? Label it with x, because we're modeling x here. So we got two possibilities. One is the distribution centered at 5.4 at the spread of 0.4. So this distribution in the null is going to be narrower and to the left of the distribution in the alternate. So what I like to do, I'm just going to kind of draw a sketch here of the two curves. It's hard to draw the sketches and then label. It's easier to draw the curves. I'm sorry, it's harder to label the axis or scale the axis and then draw the curves. But the basic idea here is that I want to create two distributions. One of them, this one's centered at 5.4. And notice I tried to draw that one a little bit narrower. And then this one's centered at 6.4. Okay. And let's see, halfway, what's halfway between 5.4 and 6.4? 5.9. So there's the half unit scale. So I'm just going to, again, give a rough scaling here. Let's see, 4.9 say, right? Okay. So now let's talk about the null and alternate for a minute, because ultimately what I want to do is calculate a p-value. So later on in the book, or later on in the problem in this example, it's discovered that there's a 5.2 centimeter pine needle on the suspect's coat, right? So I need to know, if I'm going to calculate the p-value, there's three things I need to know or have. An observed value, okay, I got that. Two, the null distribution, okay, and then three, direction of extreme. So What was the null? X is normally distributed, the mean of 6.4, that because we're saying that this is species B, that this pine needle is a species B pine needle. Then the alternate is X is normally distributed with a mean of 5.4, oops, 5.4 and a standard deviation of 0.4. And this is the species A. So this is the null distribution. This is the alternate distribution. So notice, again, let's talk about the direction of extremes. So as we move to the left on the axis, pine needle links under the null hypothesis become less common, right? Because there's a downward trend here. At the same time, more common under the alternate. So the direction of extreme here is one-sided to the left. So now, if I go and I put my 5.2 on the axis, the p-value is going to correspond to the relative frequency or the proportion of pine needles that come from species B pine trees. So the p-value is equal to the proportion, let me write it this way, of x values less than or equal to 5.2 under the null assumption, and we're going to calculate this using normal CDF. Lower limit, I'm going to use a shorthand notation, negative E99. Okay, that is the same thing I used before. That's negative, well actually that's negative 10 to the 99th power is what that represents, okay? Very small number. And then up to the right-hand boundary of 5.2, and then we put in the mean of 6.4, and then we put in the standard deviation, which is 0.5, and that's going to give us the p-value. So let's go back over here to the calculator, and we'll actually calculate this p-value. And did we already do that? Maybe. Let's see. Is that the last calculation we did? Negative E99. Oh yeah, 5.26.4.5. So the p-value, so again, when I enter all that into the calculator, the p-value is very small. The p-value is about 0.8%. So as a juror, I suppose, as a statistician, you'd be interpreting that. You'd say, well, if this pine needle came from a species A pine tree, then there's only about a 0.8% chance that we would have sampled it. So it's much more likely it came from a species A tree. And then I guess the jury is going to have to process that information and make a decision. Now, one of the other questions that I want to investigate here are this idea of these links of species A and B and species A and B pine needles. We are assuming that these links are normally distributed, and the problem here is how do we know that? How do we know that these are normally distributed? Well, having some data is helpful, okay? Because we've actually got a process we can go through to assess normality, okay? So suppose you've gathered some data on a characteristic of interest. Now, assessing normality depends on having data, okay? So when we have data, then we can use this process to assess how likely it is or how reasonable the normality assumption is. So here are the things we could do. We could look at a histogram or a stem and leaf plot. I usually use the histogram because the calculator draws the histograms. And what we're looking for is non-normal features, outliers, gaps, a pronounced skewness. So when we have a histogram that's roughly symmetric, mound-shaped, is sometimes what we call it, and there are no outliers or no obvious skewedness to that histogram, then we would say, well, that histogram gives us no evidence to contradict the normality assumption. The other thing we can do is use this empirical rule. So we can calculate the intervals, okay, x bar minus s, x bar plus s, and we should see about 68% of the data falling within that interval if the data came from a normal distribution, and about 95% within 2 standard deviations of the sample mean, and about all of the data within 3 standard deviations. Okay, there's another way to assess whether or not the data is normal or normally distributed. Now, there's another graph that we can use too, which is called a QQ plot or a normal probability plot, and the calculator will draw this. This is one of the built-in statistical plots. And what this is it's basically a scatter plot of the actual data as against the ideal values from a normal distribution, okay? If the points fall on a straight line, okay, then we would conclude a normal distribution is a reasonable model. But as the points deviate from that straight line, it tells us that there are departures from a normal model, okay? So let's take a look at an example here and assess the normality. So we got a number, let's see, the data here are the number of home runs hit by American League home run leaders in the 39 years from 1949 to 1988. So what we want to do is try to figure out, does this data come from a normally distributed population? So the first step is to enter the data into the calculator, and I haven't done that for this example, so we'll work through this together. So I'm not interested in archiving this data. I just press stat. I'm going to press enter to go to the editor window here. And let's see, I'll just insert L1 because it's not in my, whoops. Let's see, second one for L1. Okay, I'll just put that into my editor here, and then I'll clear it out. So now I have a list. Now you didn't need to go through all that if you already had L1 in your window. And I'm just going to enter the data, one data value at a time. Let's see, how many 32s? 1, 2, 3, 4, 5, 6. I got 1, 2, 3, 4. I need 2 more. Okay, I think I got all that data in there correctly. I'll just go back through real quick and double check. 1, 2, 3, 49s. Wait a minute now. 1, 2, 3, 4 49s. Okay, so I'm missing one. So let me go second, insert 49. So I'll go back through it backwards again. I'm going from the back. I'm just checking to see that I entered all the data correctly here. Okay, very good. All the data is entered. Now, I'm going to draw. First thing I'm going to do is draw a scatter plot. So I'm going to go second stat plot. I'll choose plot 1. I want to draw a histogram. So let's see, I'm going to clear out the X list that was in there and put in L1. Now I need to set up the window. Oops. All right, my calculator does that sometimes. All right, let's set up the window. So, all right, so 22 is the smallest data value. I'll start my window here, my X-min at 20. I need to get to at least 61, so I'm going to count by 5. So I'm going to end at 65 and make the X scale 5. And then Y-min of 0 makes sense. And how about a Y-max of, I'm going to guess here, I'm going to guess 20. I think 20 is probably too big. And then Y scale, I'll just make that 5. All right, so this histogram looks pretty good. I mean, 20 is probably a little big. I could go in for Y max. I'm going to go back in and just make a quick adjustment here and change 20 to 15. Will give me a little better looking graph. So that looks good. So that histogram's looking roughly bell-shaped. Roughly bell-shaped. Okay. And the other thing that I'm going to do, okay, I'm going to go ahead and I'm going to copy that screenshot into PowerPoint for reference. And let's see, the other thing I'm going to do, let me make that a little smaller. Okay, we'll come back to that. And then let's go back here and let's do the normal quantile plot. Second y equals, okay, I'm going to go back to plot 1. Now, the very last icon out of the 6 is this normal quantile plot or QQ plot. Okay, and I want to do the plot on list the data in L1, so that all looks good. Now, I have to rescale my axes. A zoom 9 works well for the normal quantile plots. Okay, and like I'm seeing a little bit of a deviation here, but it's nothing that I'm going to trigger that's going to trigger me to reject the normality assumption. So let's just put this particular calculator screen in here as well. Okay, just for reference, we can refer back to this. And then the other thing I want to do while I'm on the calculator is I want to calculate the mean and the standard deviation. So I'm going to go stat, calculate 1var stats, and the data's in L1. So I'm going to put L1 here and press enter. And let me take a screenshot of that as well. And I'll paste that into my window. All right, and let's see. So those are the calculator steps, but now let's take a minute here and talk about these graphs, or these 3 pieces of analysis. All right, that looks pretty good. All right, so we'll go back to PowerPoint now. Okay, so we just went through and did the 3 different parts of assessing normality. And what we're assessing here is the assumption of normality. Now, okay, let me think for a second. I forgot something. I forgot what scale I put. I'm going to draw my, graphs are useless unless we actually have a scale. Let's see, I went from 20 to 65 by 5s. Okay, so The reason I went through that is because I wanted to know, how am I going to scale this graph, this histogram? So we started here at 20. So this bar was at 20. This is 25. This is 30. This is 35. This is 40. This is 45, 50, 55, 60, 65. Okay, and then this y-axis is scaled as follows: 5, 10, 15. Okay, so let's go through the analysis here. So I've got the sample mean is about 41 roughly. So 41 is right about here. Okay, so there's the fulcrum point. That's where the distribution would balance. So this is approximately 41 for the sample mean. Okay. And one of the things that I'm thinking about, now remember when we were talking about the normal distribution, okay, is that if this particular data set came from a normally distributed population, then we'd expect there to be a line of symmetry for that normal curve right at the population mean, okay? Now I'm not saying the population mean is 41. The sample mean estimates the population mean, that's for sure, but I don't know that the population mean is 41. I know the sample mean is, but what I'm really doing is just checking to see if this histogram looks roughly symmetrical. And then actually it looks pretty good. Okay, it looks pretty good. Then the other question is, okay, I'm going and looking at the standard deviation now. Remember there's 2 on the calculator. I'm using S sub x here because I have a data set, and S is the sample standard deviation. So this is the sample standard deviation, which is what we need in our analysis because I don't have a population here. So that's about 7, roughly. I'm just using relatively easy numbers. And so the question I want to ask is, if I go about 7 on both sides, right? So that'd be about 49. So the first window I'm talking about is like the window that goes from, all right, 7. So let's see, 41 minus 7 is 34, right? And 41 plus 7 is 48, right? Okay. So does this interval span about 68% of the population, or of the, I'm sorry, not population, but of the data? Because again, if this data came from a normal distribution, then we would expect to see about 68%. Not exactly 68%, but approximately. So here's 48 on the X scale. Now I could go through and actually count these. This is 48 on the X scale. Here's 34 on the X scale, but I'm kind of eyeballing it and saying, does this look like it's spanning about 68%? It looks pretty good. Now, the other thing I can do, since this particular data set is sorted, I can go and see, all right, so the first part of the data that is within the interval 34 to 48 is 33. So 33, 36, 37, 43, 44, 45. Now I'm including 48. And again, I rounded this number off, but I'm just going to go ahead and fence it off there. And you know, this is an approximation. We're not going to expect to get exactly 68%. So how many data values are here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So we got about 26 out of 39. And what is that? That's about 67%. Pretty good. And so then we could look at the 2 standard deviation window. Okay, and again, I'm using just rounded numbers here. So 34 minus 7 is, what is that? 27. And 48 plus 7 is what? I think that's 55. So this, how many data values what proportion of the data set does this interval span? Well, 27 is going to fence us off right there. 55 is going to fence us off right there. So there are 2 outside that particular interval. So let's see. So 37 out of 39. 37 out of 39. What percentage is that? Well, that's about 95%. This is looking good. And then, of course, if we create the next interval, well, let's see, let's just do it. So that would be 27 minus 7 is 20. 55 plus 7 is 62. That would span now the entire data set. So we would have 39 out of 39, which is 100%, which is pretty close to 99.7 for sure. And then the other thing I'm looking at is a normal quantile plot. And as I eyeball this, I see that these values are deviating a little bit away from the line, but that's not enough to reject the assumption of normality. So overall, I'd say it's very likely that this data set came from a normally distributed population, or at least I would say there is no, okay, so the conclusion here is there's no evidence that the data did not come from a normally distributed population. Okay, well, that's it for this lecture. I hope you have a good day.